Welcome back. Let's continue looking at energy. Hopefully we've had something to drink, or we've gone and had a quick run around and we've got lots of energy for this. So, let's investigate kinetic energy. Okay, so here what we're going to do is I've got a little animation. All right, it's all about stopping distance, but we're not worried about this. I just want you to see what happens when the cars move. So, we're going to look at the first car. And, oops, no. So only this top one's going to go. Watch. It runs. We're not worrying about what happens with the other cars. And it's going very, very, very slowly. So because it's going very slowly, it stops quite quickly. So it doesn't have a lot of kinetic energy. Let's reset. So now we're going to have two cars. Now this car's going faster. So now I want you to watch. Okay, it's going to go, then it's got to stop, and, oh boy, but it had more kinetic energy to start off with, so it travels far further, because it was faster, okay? Let's go to 3, oopsie, let's go to 3. Let's see what happens. See, that one's going much faster now. And it goes, just keep going, it's going. And there it goes. It stops. Smallest kinetic energy, bigger kinetic energy, even bigger kinetic energy. Okay? Let's see if we now have 4. So we have 4, they're starting a bit further, just so they're going faster. And let's see, they all get there at the same time. And it's going further and further and further and further and further. And eventually it stops. There we go. Okay. The faster it was going, the further it traveled. Okay. So now what we need to do is when we come back here, okay, what I needed you to see with this is that we kept mass constant, okay? So we kept the same car, but every time we did it, we had the same car was going faster. The faster it went, the further the distance it traveled, okay? So when we look at this, it means that it had more kinetic energy. Mass does affect kinetic energy, but speed is very important. And in fact, the velocity that it's going at is more important in terms of how it changes the kinetic energy than the mass is. Okay? Because if we look at the equation, we know that EK equals a half mv squared. The half is a constant. That's not going to change. We're not going to worry about how we got to the half. That doesn't matter. But mass is directly proportional to the kinetic energy. So bigger objects have bigger kinetic energies when they're moving because they've got a bigger mass. Smaller objects will have smaller kinetic energies. That's a direct proportion. If mass doubles, kinetic energy doubles. If mass becomes 3 times smaller, kinetic energy becomes 3 times smaller. That's an easy relationship. Kinetic energy and velocity, this one's a little more complicated because it's v squared. There's also a direct proportion, but kinetic energy is directly proportional to the velocity squared. So if velocity doubles, kinetic energy becomes 4 times bigger because we went 2v, 2 squared is 4. So we've got to keep that in mind, which means for us that a change in velocity has a much bigger effect on kinetic energy than a change in mass does, okay? So, these are the relationships we were just talking about. Kinetic energy, directly proportional, remember this sign means directly proportional there we go, to v squared. And it's directly proportional to mass, so the two of them go together, okay? Let's look at potential energy, and again, I've got something to show you, but we're going to do some calculations with it, so I'm going to get that side ready, and here we go. So here we have a scientist who is going to drop a ball from a height. At the moment, it's at 3.6 meters above the ground. I'm not going to worry too much about the time, okay? That's not why we're doing this. We're going to look at the potential. So now I have a tennis ball, which is 59 grams, okay? So I'm going to drop the ball. There we go. So the ball drops, and then it bounces, and it stops at 2 meters, all right? So if we go back here, what we knew was the mass of my tennis ball was 59 grams. Remember, in physics, we can't work in grams. We have to work in kilograms. So I'm going to divide that by 1,000, okay? And just in case, let's just quickly do 59 divided by 1,000. Oopsie, gives me 0.059. So that's the tennis ball. The original height was 3.6 meters, okay? I can work out how much potential energy it has. So I can go potential energy is mass times gravity times height. The mass is 0.059. Gravity is always 9.8. That was 3.6. Absolutely need a calculator now. So we've got 0.059 times 9.8 times 3.6, 2.08 joules, okay? We then saw that it went back up to a height of 2 meters. So if I now change this height to 2 meters, we now need to say to ourselves, well, will the potential energy change? Height has changed. So what the potential now becomes, mgh, so 0.059, we've got 9.8 times 2 this time. Have to use our calculators. All right, so let's do the calculation, and we get 0.059 times 9.8 times 2, and has to be a decimal, so we've got 1.16, because we're going to do to 2 decimal places. Now, here we can see that I changed the height, so I changed the potential energy, but let's see if we can get something that's a little bit more, whether they're directly proportional or that sort of thing. So we're going to go back to our little man. Okay, there he is. And we're going to reset, and I'm actually going to drop him down. So at the moment he's 3.6. If I take him down to 1.8, so he's going down, it's taking him a while. So what I'm doing is I'm going to halve the distance, at least I hope I can get there. I'm not sure I can, actually. Can he go that far? No. Okay, so let's take him back up to, that'll do. No, let's take him back up, we'll do mass instead, because that'll be easier. So here we go up, he's going up, he's going up, he's going up. Let's stop him at 3.6. Let's use something other than a tennis ball. Hockey ball. 50, we did it 59, now we've got 162. That's about 3 times bigger, okay? Not quite, it's about 2.5. Actually, let's just check how many times bigger it is. So I'm going to take the 162 divided by 59, and it's 2.7, okay? That's a nice sort of round number. So what we're going to do now is we're going to drop it from the same height as we did the last one. So let's just get rid of that. So now we're going to drop it. And he hits the ground. And interesting, do you see it doesn't actually go as high? That's quite an interesting, that's about energy changes and what happens when it hits the ground, okay? Because the hockey ball is harder, it's heavier. There's a whole bunch of things that happen here that we're not worried about right now. So let's go back to our calculations. And what I'm going to do here is let's get rid of this. I'm now going to do the calculation with the 1,62 grams. So my mass was 162 grams. So that's 0,162, okay? On the calculator, we realized that the difference was 2,75. I'm just going to put that in the corner for us to keep note of, okay? Just putting that there for now. Now we can go EP equals MGH 0,162 times 9,8. The height was 3.6. Let's calculate that quickly. 162, there we go, times 9.8 times 3.6. And we get 5,72. All right, so heavier mass, bigger potential. Now what I'm going to do here is I'm going to take that 5,72, divide by the 2,08, and see if I get 2,75. And then I'll explain to you why I'm doing that. So 5,72 divided by, and it was 2,08, 2,75. What that means for me is that potential energy is directly proportional to the mass. The mass changed by a factor of 2.75, energy changed by a factor of 2.75. So, potential energy is directly proportional to height, and it's directly proportional to mass. If one increases, the other increases. If one decreases, the other decreases, but by the same amount. If height doubles, potential doubles. If mass is 2 times smaller, potential is 2 times smaller. Okay? With mechanical energy, I just need you to remember that mechanical energy is EP plus EK. There's no direct proportionalities here, okay? So I can't say if potential doubles, mechanical energy will double. Why? Because of the plus sign. What I can say to you, though, is if potential energy gets bigger, mechanical energy will get bigger. If kinetic energy gets bigger, potential energy, mechanical will get bigger. But I can't use the word directly proportional, okay? But they are proportional. So in other words, if I increase EP, E mechanical will also increase. But I can't say by the same amount. The same happens if I increase EK. Okay? We are going to look later on at the relationship between those two and how mechanical works, how mechanical energy works. But for now, It's just about the fact that they increase together or they decrease together.